This is lesson 7.1, Eigenvalues and Eigenvectors. This begins the last chapter in our linear algebra journey. And so we're gonna look at these eigen things, these eigenvalues, eigenvectors, eigenspaces. And before we even take a step further, let me just kind of step back and talk about this word eigen, because I think sometimes there's just like this, maybe this idea of like, well, mysterious eigenvalues and eigenvectors. But the word eigen is actually just German and simply means own, O-W-N. The use in here actually comes from eigenwert, which means proper value. So whenever you see eigenvector, eigenvalue, eigenspace, all we're talking about is really just kind of this relationship between these three ideas that have a very kind of a special or unique or proper relationship between them. And you'll see that as we go through this lesson and the other two lessons to come. So with that, I had mentioned at the end of lesson 6.4 that kind of a pinnacle question in linear algebra it's actually called the eigenvalue problem, is this, and I'll state it this way. Is it possible to find a square matrix A vector x, and a scalar such that I could multiply the matrix A times x and the scalar times x and get the same result in both cases? That's basically the eigenvalue problem in linear algebra. And so we're going to investigate that in this lesson, among a few other things, but that'll be kind of a focus of what we do here. So with that, let's go ahead and define what an eigenvalue and eigenvector are. So it says A is an n by n matrix. The scalar lambda is an eigenvalue of A when there is a non-zero vector x such that A times x is equal to lambda times x. So this is that eigenvalue problem. This is what we're looking at right here is, can I find a matrix A, multiply it by x, and a scalar lambda and multiply it by x and get the same result on both sides of the equation? So lambda is the eigenvalue. The vector x is the eigenvector, okay, of A corresponding to lambda. What you'll find as we go through this is that, and it says here in the notes, that a matrix can have more than one eigenvalue. So when we talk about eigenvalues and eigenvectors, again, remember I said there's a relationship there. And in this case, if for each eigenvalue that you find, you have to find, or there exists corresponding eigenvectors that are specific to that value of lambda. All right, so what exactly does this kind of mean? Let me kind of do a kind of a pictorial or graphical representation of this. So if I take a vector, and I'm just going to put that vector into the first quadrant, we're going to call this vector x. If I multiply that vector by a scalar, in this case lambda, it's simply going to create a parallel vector either in the same direction of vector x or in the opposite direction. So I'm going to end up with a situation, for example, maybe I have a vector that looks like this, where the whole thing, right, this whole vector is some scalar lambda times x. In this case, lambda being greater than 0, pushing it in the same direction as x. If lambda is negative, it's going to have the same effect of either stretching it or shrinking it, creating a different size vector, but in the opposite direction. So this would also be lambda x, but in this case, lambda would be less than 0, flipping it 180 degrees, moving it in the opposite direction. Okay, so that's what the right side is doing. We're just taking a scalar times a vector. That's what it does. So the question then is, there a matrix A that we could find that would have the exact same effect? Okay. All right. Also, I should note that x cannot be 0. The vector itself cannot be 0. That kind of makes this whole thing pointless, because then you're always going to have 0 equals 0 no matter what A and lambda are. All right. So let's go ahead and let's take a look at our first example, which is just simply to verify this relationship between an eigenvector and an eigenvalue. So we're going to start with matrix A, and we're going to say A equals 2, 0, 0, negative 1. And we're going to verify that if x1 is 1, 0, then the eigenvector of A corresponding, or is an eigenvalue of A corresponding to eigenvalue lambda 1 equals 2. This is really two questions in one. So we're going to do that, and then we're going to do this a second time. And we're going to take x2 to be the vector 0, 1. And that's an eigenvector of A corresponding to the eigenvalue lambda 2 equals negative 1. All right, so all this is asking us to do is just really to show that if I multiply A times x, that I can simplify that down to a scalar times x as well. So we're going to start by taking A times x1. We're kind of doing this part first. This is one question, and then this is another question. So we're going to kind of do these in two separate passes here. So A times x1, A is 2, 0, 0, negative 1. And x1 is 1, 0. So if I multiply those together, I'm going to get the vector 2, 0. Now, remember, we're trying to write a scalar times x in this case. So in this case, here's x, right? This is A, this is x, and right now this is A times x. If I factor out a 2 from that matrix, I can write 2 times 1, 0. Well, again, 1, 0 is x, and now I'm multiplying by a scalar 2. That's our lambda. So in this case, on the left-hand side, I took A times x. I took a matrix times the vector. On the right-hand side, I'm taking a scalar times a vector, and I'm getting the same results. So again, here then, x would be our eigenvector, and lambda would be the eigenvalue. Okay? All right, let's do this again for the other one. So the other one, same idea. We're going to take A times x2. So again, we're going to take 2, 0, 0, negative 1, and multiply that by, in this case, 0, 1. And if we do that, we get the vector, let's see, we'll have 0 and negative 1. So again, I want x, 0, 1, and then I just need a scalar that's going to give me 0, negative 1. Well, that's just negative 1 in front. So again, A times x is equal to lambda times x. All right. So that's the idea. That's the whole idea behind these eigenvectors and eigenvalues. All right, let's move on then, and let's go through a theorem, and then we'll get into some more examples here. So it says that if A is a square matrix with an eigenvalue lambda, then the set of all eigenvectors of lambda, together with the zero vector, we've got the mathematical symbology there, is a subspace of Rn. This subspace is an eigenspace of A. So here we get this third term now, this idea of an eigenspace. So it says we've got a square matrix with set of all vectors of lambda together with the non-zero is a subspace of Rn. And the subspace is just the eigenspace. So again, let's just take a look at an example to make sense of what this is actually saying. We're gonna do two examples. I'm gonna do one example, and then we're gonna see another theorem, and then I'll do a second example. But in both cases, we're looking at finding the eigenvalues and eigenspaces. For this first one, though, we're going to take a more of a geometric approach. So this is kind of atypical. You don't typically go through this process, but I want you to see kind of another way to approach this when it works. So we're going to find the eigenvalues and corresponding eigenspaces for the matrix A equals negative 1, 0, 0, 1. Okay. So like I said, we're going to take a geometric approach to this one. And what I mean by that is if you look at that matrix A, it may or may not look familiar to you, but we saw that matrix back in the last lesson of chapter 6. This matrix A is what causes a reflection in the y-axis. If I take this matrix and I multiply it by vector v, vector v just being like xy, if I take negative 1, 0, 0, 1, and I multiply it by xy, it's going to give me the vector negative x, y. And so if you think about what that is geometrically, in our coordinate system, if I have a vector, again, I'll just put in the first quadrant with coordinates x, y, the coordinates negative x, y are going to take me exactly in the opposite direction. So that's going to give me a vector here at negative x, y. Now, in order to find the eigenvalues and the eigenvalues and eigenspaces, what we're going to do is we're going to break down this vector into its vertical and horizontal components. So I'm going to think of xy as having a horizontal component, x0, and a vertical component, 0y. Okay? So again, if we think about reflecting those components, x0 would reflect to negative x0, and 0y is going to stay right where it is, right? It's on the y-axis, we're reflecting in the y-axis, it's not going to move. So for the vector on the y-axis, the x-axis, we'll start with that one. If I take negative 1, 0, 0, 1, and I multiply it by x0, I get, as expected, I get negative x0, right? I get the reflection in the y-axis. Now again, thinking about this in terms of eigenvalues and values and eigenvectors, I want to be able to write this as a scalar times x. So in this case, if I pull out a negative 1, I can write this as, if I can think of this as a and x, and this is lambda and x. So in this case, then, our eigenvalue is negative 1. Lambda is negative 1. Okay, that's going to be our eigenvalue. I will summarize this a bit more in a minute, but let's do the same thing for the y-axis. Let's find its eigenvalue. So for the vector on the y-axis, again, same idea. We're just going to take a, which is again negative 1, 0, 0, 1. And now for the y, we're going to multiply it by 0y. And that's going to give us, as expected, 0y. Because again, that point doesn't move under the reflection in the y-axis. Which in this case then, I'm really just multiplying that vector by 1 to get an equal statement. So in this case then, lambda is 1. So those would be our eigenvalues, 1 and negative 1. So because of that, we can say that the eigenvectors, I'll write this out, it's going to be a little bit of writing, but the eigenvectors corresponding to lambda 1 equal negative 1 are non-zero vectors on the x-axis, and the eigenvectors, in fact, let me just do this, the eigenvectors corresponding to lambda 2 equaling 1 are the non-zero vectors on the y-axis. In other words, then the eigenspace, so the eigenspace, remember, is, we define that up above, right, is the subspace of A, and so, or excuse me, the subspace of Rn. So in this case, the eigenspace corresponding to lambda 1 equals negative 1 is the x-axis, because if my eigenvectors are all non-zero vectors on the x-axis, then the x-axis contains all of those vectors. That is my eigenspace. And then likewise, the eigenspace corresponding to lambda 2 equaling 1 is the y-axis, because again, it contains all of the eigenvectors for that lambda value. Okay, so like I said, that was a geometric approach, not very typical. But if you were to see that, if you were to see in A, that idea that there's, some kind of transformation occurring, you could take that approach and do it that way. Now, obviously, you could also do a straightforward algebraic approach, and we're going to look at that in just a moment, how to do this algebraically. But I just wanted you to see kind of a slightly different way to do a problem like this. All right, so here's a theorem that says, let A be a square matrix. An eigenvalue of A has a scalar lambda such that the determinant of lambda times the identity matrix minus A is 0. Okay, so this is the eigenvalue, is basically finding that. And then the eigenvectors of A corresponding to lambda are the non-zero solutions to this equation. Okay. All right, so again, just a note here. It says the equation for the determinant is a characteristic equation of A. And if you were to actually algebraically multiply out or calculate out that determinant, and we're going to do that, what you end up with is a polynomial. And that polynomial is called a characteristic polynomial of A. The eigenvalues of the square matrix A correspond to the roots of that polynomial. So bottom line, here's what we're going to do. We're going to take, to find the eigenvalues, we're going to take this determinant, we're going to find we're going to convert it into a polynomial. We're actually going to calculate the determinant, creating this polynomial. We're going to find the zeros of that polynomial, and those zeros are the eigenvalues. And then once we have the eigenvalues, we can then use those to find the eigenvectors by solving this equation, because we would now know what lambda is, and we can actually set up an equation where we just really have the one variable x. Okay? All right, so let's go ahead and let's do that. So like I said, so we looked at a geometric solution, and this could be done in the way that we're about to do, and this is the more common way to approach this, is doing this algebraically like this. So we're going to find the eigenvalues and the corresponding eigenvectors for the matrix 2, -12, 1, -5. So in this case, we're going to start, like I said, by applying this thing right here. We're going to find the determinant of lambda I minus A. Now, right now, we don't know what lambda is. That's what we're trying to find. So when we do this, what we're really doing then is we're finding the... we're going to find lambda by, again, making the matrix, or not the matrix, the polynomial, and then solving that polynomial, finding its zeros. So the determinant is lambda times the identity. So if you think about that identity, in this case, we've got a 2 by 2, so 1, 0, 0, 1. So it's really just lambda minus 2, and then 0 minus the -12 is a positive 12. And then 0 minus 1 is a -1. And then lambda minus the -5 is lambda plus 5. So now we're going to actually solve or find that determinant. So for a 2 by 2, we simply find the determinant, or can find the determinant just cross-multiplying, kind of multiplying across the diagonals and subtracting. So we'd have lambda minus 2 times lambda plus 5, and then minus -1 times 12, which is just obviously going to be plus 12. So this, and obviously this whole thing is equal to 0. So what happens then is when I solve this, I've obviously got to simplify. This is equal to 0. So now I'm really focusing on this part of it. So I'm going to multiply out the left side and put this into standard form. So we've got lambda squared plus 5 minus 2 is plus 3 lambda. And then minus 10 plus 12 is plus 2. And that is equal to 0. Let me get rid of that equal so we can kind of see that equation. So this is the polynomial that we're solving for lambda. We're finding the roots or the zeros of this function. So to do that, let's refactor it now. And so we'd have lambda plus 2, lambda plus 1 equals 0. And so lambda equals -2, and lambda equals -1. These are our eigenvalues. Okay. So now that we have the eigenvalues, for each of those, we have to go through now and find the corresponding eigenvectors. So let's start, for example, with -2. That's listed first, so we'll just start there. So for lambda, we'll call this lambda 1 equals -2. We're gonna solve, in this case, lambda I minus a times x equals 0. But we know now that lambda is -2. Okay? So what this looks like now is -2 times I minus a is going to be, so again, thinking about 1, 0, 0, 1. -2 minus 2 is 0. Or I'm sorry, -2 minus 2 is -4. 0 minus -12 is a positive 12. And we've got 0 minus 1 is -1. And then -2 plus 5 is 3. So we want to reduce this down now to a reduced row echelon form. And so if we do that, we're going to get the matrix -1, -3, and 0, 0. Notice that the two rows are just multiples of each other. And so one just cancels out. We get 0, 0, and then the other just reduces to 1, -3. Okay, so remember, this is technically being multiplied then by x1, x2 equals 0. That's really the equation that we're solving to find the eigenvectors. And so what we have then is we've got x1 minus 3x2 equals 0. That's the only equation we get out of this. And if I let t equal x2, then that means that x1 would have to be 3t. Right? So then kind of think back to how we've done this before in the past. So what I have then is x is just x1, x2, which in this case then x1 we said is 3t, x2 we said is t, and if I factor out a t, I get t times 3, 1. Obviously t cannot be 0 in this case, or again it would just be pointless. So in this case then, my eigenvector that corresponds to lambda 1 equaling -2 is the vector 3, 1. Okay. So now we have to do the same thing for lambda 2, which is -1. So we'll call this lambda 2, -1, and we're going to do the same thing. We're going to solve that equation. So in this case, we're going to take -1. I'm going to kind of shortcut just a little bit here. -1 times I minus a. And in this case, let's see here. Can I do this in my head? We're going to get a -3, a 12, a -1, and a 4. And again, notice that those two rows are multiples of each other. And so one is going to cancel out. That bottom row, if we just change the signs, is 1, -4. So that would be reduced row echelon form. So again, same idea. So x in this case. So let's see here, I would want, if we think about like x1 minus 4x2 equaling 0, if I let x2 be t, then x1 has to be a 4t. So I'm going to have 4t and t, which is just t times 4, 1. So in this case, then, our eigenvector is 4, 1. Okay? So eigenvector 3, 1, 4, or that corresponds to the lambda value of -2. And then this is the eigenvector that corresponds to the lambda value of -1. Okay? So that's how you solve these algebraically. That's how you find the eigenvector and eigenvalues algebraically. And like I said, we could go back to that previous example that we did geometrically and do the exact same thing with that. All right, well, let's move on here. And so this is kind of just the process summarized. And so I'm not going to go through this. Like I said, this is just exactly what we did. It just kind of walks through the steps. But you've got that for your reference then if you need that. All right, so let's do another example here. We're going to do the same thing just to get another example in, just to really see how this works again. So we're going to find the eigenvalues corresponding to the eigenvectors of the matrix A. And then we're going to find the dimension of the eigenspace of each eigenvalue. All right, so like I said, same idea. We're going to, in this case now, do the same thing. We're going to find the determinants of lambda I minus A, which in this case now we've got a 3 by 3, which we're going to take lambda minus 2, -1, 0, and then 0, another lambda minus 2, and 0, and then 0, 0, and yet another lambda minus 2 at the end. All right, well, if you remember how to find the determinant of a 3 by 3, you have to pick either a row or a column, multiply the elements in that row or column by the determinant of kind of what's left when you cross off the row or column. So, for example, if I just pick, I notice that there's, in this first column, there's 2 zeros here, so let me just pick that column. I would take lambda minus 2 times the determinant of what's left. So what's left, if I cross off that row, cross off that column, what's left is this 2 by 2, which the determinant is just, oops, let's cross that off. Let's delete this because we can actually calculate this. The determinant is just x minus 2 squared, or not x, lambda minus 2 squared minus 0. So that ends up being that part of it. Then we technically have to go through the zeros also, but obviously 0 times the determinants is just 0, so we don't need to bother with those. So that's why you pick the zeros, remember, is then you don't have to deal with those. You just have to deal with the non-zeros in that row or column. So this is the determinant, which I'm just going to simply write lambda minus 2 cubed. So that's the determinant of lambda I minus 2, which means that in this case, lambda, our eigenvalue, is simply 2. But we're going to say that it has multiplicity 3. You may have seen that before. May have talked about when you're solving polynomials, you get a 0 that occurs more than once, which is exactly what's happening here. We just say it has multiplicity 3. It's a 0 that occurs 3 times. All right. So now we have to go through and find the corresponding eigenvector. Now in this case, we don't have to obviously do this 3 times. We just do it once for 2, and that's all we have to do. So in this case, we're going to do 2i minus a, which gives us the vector 0. Kind of a shortcut to doing this is if you look at the determinant that we set up here, if we look at this determinant here, just plug 2 in for lambda, and that's basically going to give you the matrix here. So plugging in 2 for lambda gives me 0, -1, 0, 0, 0, 0, and 0, 0, 0. That was a lot of fun. All right. So, but it does give us an equation. It gives us the equation -x2 equals 0, or just simply x2 equals 0. So that means that x1 and x3 can kind of be, I guess, whatever they want. So x1 we'll just call s, and x3 we'll call t. So then x, again, we'll kind of formalize this one this time, is really the vector x1, x2, x3, which in this case then x1 is s, x2 is 0, x3 is t. That's an s. Hopefully you can, not a 5. My s's and 5s always look the same. Very, very difficult. All right, so in this case, let's split this up into 2 separate vectors. Let's call this s times the vector 1, 0, 0. We'll do this as a linear combination, plus t times the vector 0, 0, 1. And again, s and t cannot be 0. So in this case, then our eigenvectors are 1, 0, 0. These right here give us our eigenvectors, and 0, 0, 1. Okay, so again, that is corresponding to lambda equals 2. In this case, we have 2 eigenvectors, and that is our dimension. So our dimension is 2. That was the other part of this question. Okay. Now, one thing I want to point out, and we'll see this kind of as we continue to go through other examples, the dimension of the eigenspace is always, let me flip this around and say it this way. The multiplicity of lambda is always greater than or equal to the dimension of the eigenspace. So in this case, we had a multiplicity of 3, which means that our dimension has to be less than or equal to 3. In this case, 2. Just kind of an FYI to keep in mind, kind of a little check to make sure that you've done things correctly maybe. All right, let's go ahead and let's keep moving on this. So another example here. We're going to, again, find eigenvalues. We've got a bigger vector now, or a bigger matrix. We've got a 4 by 4. So we're going to find the eigenvalues and the bases, or the basis for each of the eigenspaces. Okay, same idea, same thing. We're going to take lambda I minus a, take the determinant of that. All right, so in this case, let's see, we've got lambda minus 1, 0, 0, 0. Then we've got 0, another lambda minus 1, negative 5, 10. And then we've got negative 1, 0, lambda minus 2, and 0. And then negative 1, 0, 0, lambda minus 3. So we have to find the determinant of the 4 by 4. Now, thankfully, there's a lot of zeros in there, so I don't think this is going to be overly difficult. I'm going to start by looking at the second column. There's 3 zeros there. And so if we look at the second column, again, all I have to really be concerned about is this x minus 1, because everything else is going to come out 0. So that's going to give me x minus 1 times the determinant of what's left when I kind of cross off those rows and columns. So that's going to give me lambda minus 1, 0, 0, negative 1, lambda minus 2, 0, and negative 1, 0, lambda minus 3. All right, so we've got, I'm sorry, that should be a lambda, not an x. So we've got lambda minus 1. All right, so now the determinant of this 3 by 3, well, again, if I take the first row, because I've got 2 zeros there, I just really need to focus on that times the determinant of this part. Well, notice what happens is I take lambda minus 1 times the determinant of that 2 by 2, which is lambda minus 2, lambda minus 3, and the rest is 0. So again, works out really, really nicely. In this case, then we have 3 eigenvalues. We have lambda 1 equals 1 with multiplicity 2. We have lambda 2 equals 2, and we have lambda 3 equals 3. So again, now we'd have to go through for all 3 of these lambda values. We have to find the eigenvectors like we've done before. So in this case, I'm just going to do it for one of them. I'll give you the others and then leave it to you to decide if you want to try to verify those for some extra practice. So let's just start with the first one here. Let's take lambda 1 equals 1. And so for that one, so we'll do that one. Let's take 1 times the identity matrix minus A, and that is going to give us the matrix. All right, so again, the kind of little trick, just plug 1 into your lambdas and that large determinants. We're going to get zeros across the first row, 0, 0, 0, 0. In the second row, we'll have 0, 0, negative 5, 10. In the third row, we've got negative 1, 0, negative 1, 0. And in the last row, we'll have -1, 0, 0, -2. All right, so again, we always want to row reduce these. So I would just use a calculator for this, punch it in as a 4x4, find the reduced row echelon form, or use software, whatever you want to use is fine. And the reduced row echelon form is this, is 1002, 001, -2, and then 2 rows of zeros, 0, 0, 0, and 0, 0, 0. Okay, so in this case, let's let x4, since that's common to both rows, let's let that be t. And in that case, then, that means that x1 would have to be -2t. x2 would have to be a positive 2t. And because there's nothing for x2, or I'm sorry, that should be an x3, right? x3 is 2t. And because there's nothing in column 2 for x2, we'll just give that a different letter. We'll just call that s. Okay. So in this case, we've got x is, again, x1, x2, x3, x4, which is, so x1, we'd call this basically, we'll do this with a -2t. x2, we said was s. x3 is 2t. And x4 is t. So again, writing this as a linear combination of s and t. For the first one, we'd have 0, 1, 0, 0. And then plus t, -2, 0, 2, and 1. So again, those are the eigenvectors, and that actually creates the basis for the eigenspace. Okay, so in this case, our basis would be 0, 1, 0, 0, and -2, 0, 2, 1. All right. All right. Like I said, we'd have to do the same thing for alpha or lambda 2 and lambda 3. So let me just give you those. So for lambda 2, which is 2, if we go through that process, our basis that we would get, again, just same process we just did above, we're going to get the basis 0, 5, 1, 0. And for lambda 3, which was 3, we get the basis 0, -5, 0, 1. Okay. All right. And again, if you kind of look at that, so again, 1 had a multiplicity of 2. We have 2 eigenvectors in our eigenspace, or a dimension of 2. And so the dimension is 2, multiplicity is 2, those are equal. And then same for lambda 2, lambda 3, those each had a multiplicity of 1, and they each had a dimension of 1 eigenvector. Okay. So again, just kind of not that it's necessarily going to tell you right or wrong, but it's just a little checker, a little thing that you can kind of keep in mind as you're going through these. All right, let's finish up then with one last idea here. And that is, I guess there's a quick theorem here. It says if A is a square triangular matrix, then its eigenvalues are the entries on its main diagonal. Now, let's go back a minute and let's look at example number 4. Notice that this matrix A is a triangular matrix. Remember, triangular matrix just means that you have all zeros either to one side or to the other of that main diagonal. So this is a triangular matrix. And notice then that our main diagonal, 2, 2, 2, gave us the eigenvalues. Okay. Now, if you look at the next one, it's not a triangular matrix, but it happened to just by coincidence be the same thing. Now, probably not totally by coincidence, but again, our main diagonal gave us the eigenvalues of 1, 1, 2, and 3. Okay, so it's not necessarily uncommon. You'll see that happen from time to time, but if it's triangular, it'll always be the case. All right, so now the last topic, which is eigenvalues and eigenvectors of linear transformations. Now, we're going to read through this, but understand that really going through this process there's not really a huge difference, but I'm gonna show you some connections that go back to chapter 6 when we dealt with transformations there, that are, I think, kind of cool in terms of how some of the stuff we did there to find things like A prime can be found using eigenvectors and things like that. So it says a number lambda is an eigenvalue of a linear transformation T when there's a non-zero vector x such that T of x equals lambda x. The vector x is an eigenvector of T corresponding to lambda, and the set of eigenvectors of lambda is the eigenspace of lambda. So you'll notice it's basically saying the same thing that we've been talking about. All it's doing now is just talking about in the context of a linear transformation. The math that we do, everything that we do is going to be exactly the same. Okay, so it's really just kind of saying, hey, look, you can do everything we did for just kind of generic situations. You can also apply to linear transformations as well. But like I said, I want to go through an example, and then I do want to make connections back to some things that we did in chapter 6. So what we've got is we're going to find the eigenvalues and a basis for each of the corresponding eigenspace for the matrix A, which is given here. All right, same idea as what we've been doing. We're going to find the determinant of lambda I minus A, which in this case is lambda minus 1, negative 3, 0, negative 3, lambda minus 1, 0, and 0, 0, lambda plus 2. All right, which gives us, let's see, in this case, I think I want to just focus down here since we've got zeros there. So we've got lambda plus 2, and then times the determinant of this 2 by 2, which is lambda minus 1 squared. And then I should put this in brackets here because then we've got a plus or a minus 9, I should say. So we're going to have to deal with that inner part. We've got lambda plus 2 on the outside. On the inside, we're going to have a lambda squared minus 2 lambda. Plus 1 minus 9 is minus 8. Hopefully you remember how to factor. This factors lambda minus 4, lambda plus 2. So notice again, we've got multiplicity here. We've got lambda plus 2 squared and a lambda minus 4. So our eigenvalues are lambda 1 equals negative 2 with multiplicity 2, and lambda 2 equals 4. Let me move that down so it doesn't get confused with the equalities there. All right, so those are our eigenvalues. So now again, we've got to go through and find the corresponding bases. So for lambda 1, equaling negative 2, again, we're going to take negative 2i minus a. And again, I haven't been showing this, but remember that we're always setting this to 0, which is how we're getting those equations at the end. So I've been a little lax in not being formal with that, but understand that is what we're really doing here. So in this case, we're going to have the matrix negative 3. So again, just plugging in negative 2, negative 3, negative 3, 0, negative 3, negative 3, 0, and 0, 0, 0. So again, applying reduced row echelon form, Gauss-Jordan elimination gives us Well, again, obviously those first two rows are the same. So the top is just going to reduce to 1, 1, 0, and then the rest is just going to be 0, 0, 0. All right, so that gives us the equations, x plus 1, or the equation, x plus 1, x1 plus x2 equals 0. Ooh, I think I'm getting tired here. All right, so I'm going to let, in this case, let's just call x1 s. That means that x2 is negative s. And x3, we'll have to give another letter to, we'll call that t. So again, x is, let's just go through this. x1, x2, x3. I'm going to kind of skip a step here. Let's just go right to the linear combinations here. So we're going to have an s. X1 is s, so that's 1. X2 is negative x, so that's a negative 1. There is no s in x3, so that's 0. And then plus t, which is 0, 0, 1. So our basis then, again, is going to be 1, negative 1, 0, and 0, 0, 1. All right. Again, doing the same thing for 2. And again, I'm not going to go through this one, but let me just give this to you because I do need this for what I want to show you as far as relating this back to chapter 6. So for this one, if we go through this whole process, what we basically get is x equals t times 1, 1, 0. And so our basis for this one is just that. It's just 1, 1, 0. Okay. So those would be the eigenvalues and the bases for the corresponding eigenspaces. Remember that in this case then, these vectors that we found in our bases, these are the eigenvectors. Okay? All right. Now, we started with this matrix A, 1, 3, 0, 3, 1, 0, and 0, 0, negative 2. We actually did this exact same, or used this exact same problem, or matrix, I should say, back in chapter 6. And let me just show you this example from chapter 6. This was from 6.4. Exact same matrix, 1, 3, 0, 3, 1, 0, 0, 0, negative 2. And in this case, we found the matrix for t relative to the basis B prime. Okay, so think back to chapter 6. Think about what we did here. All right, so we've got a matrix relative to the standard basis. Standard basis, again, being the 1, 0, 0. It's right here. This is our standard basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. We wanted to find a matrix relative to the basis B prime, which was a non-standard basis. Look at B prime. 1, 1, 0, 1, negative 1, 0, 0, 0, 1. 1, 1, 0, 1, negative 1, 0, and 0, 0, 1. Now, I solved mine in the opposite order, but those three vectors, those eigenvectors, create the columns for P. Here's P, and those three vectors create P. Now, if we continue on, to find A prime, to find the matrix relative to the basis, if you remember, we had a formula where we had to take P inverse times A times P. Hopefully you remember this because you've got a test on it next week. But anyway, that gives us this matrix. So A prime is this matrix right here, 4, 0, 0, 0, negative 2, 0, 0, 0, negative 2. Look at those values. 4 is negative 2, negative 2. 4, negative 2 with multiplicity 2, right? That main diagonal is the eigenvalues that we found in this problem. In other words, when you find the eigenvectors, that makes up this matrix P. So these eigenvectors are the columns, and the eigenvalues that we found make up the main diagonal for A prime. I don't know. I thought it was cool. Maybe I'm geeking out a little bit on that. Maybe you don't find it so cool. But I thought that was cool to see that connection being made between, making that connection between what we just did with eigenvalues and eigenvectors and some of the work that we did back in chapter 6, finding these matrices relative to a basis. It all kind of fits together. It all kind of comes together in a pretty cool way. All right. Well, that is it for this lesson. Hopefully you've learned a thing or two. Big thing here is obviously, really just be able to find those eigenvalues, those eigenvectors, those bases, which is basically the same thing. As always, contact me with any questions you have. Otherwise, I'll see you in the next lesson.